Okay, so this is a solenoid. A solenoid is typically a coil of wire that current flows through. And in this case, I have my current coming in and going to the right through the loop. We can kind of think about the backside there. So that's away from you. So the current comes in, goes down in the front, up in the back, down in the front, up in the back, all the way till it leaves this coil. Now then the magnetic field is pretty weak comparatively. It's not zero, but it's just very weak. So if we were to imagine that this current is coming in and going down in front of the page, up behind the page, then we could model this current for the points that are poking out of, so the current would be coming out of the page and then into the page, out of the page and into the page, out of the page, into the page. So let's model that. So here I have the into the page that represent the current at the bottom, and I have the out of the page that represent the current at the top. So if I use the right hand rule where I put my thumb in the direction of the current, so for these, my thumb would be pointing out at me and my fingers wrapping around the coil there, or the wire there. And so the magnetic field for this little bit of wire would be around the wire like that. Now, putting your thumb into the page for the X, it would go around like that. And so within this coil of multiple rings of magnetic or current carrying wire, we would get all of these magnetic fields tangent to the circle around each one of these current carrying wires would be pointing to the right. So overall, we get a magnetic field that is pointing to the right in this case, due to the combined or superposition of all the magnetic fields inside. Now, the magnetic field outside of the wires becomes or is considered very weak comparatively, because these are all superimposed in here to be very, very strong. So we've got all of these coils, all of these rings of current carrying wire, and they're creating magnetic field, and this one and this one. And then don't forget the piece that's in along the plane of the page there and behind the plane of the page there are also contributing to this magnetic field that is all to the right. So comparatively, we get a very weak magnetic field outside this solenoid. It's so weak that it's almost zero. But we do have a overall north pole and a south pole of this solenoid. So the magnetic field inside is much, 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 much greater than the magnetic field outside. Therefore, we're going to treat the magnetic field outside of the coil as being approximately zero. The solenoid is essential for creating electromagnets so that we can create a magnetic field and control the strength of the magnetic field. So there's lots of applications to this. Now let's look deep inside the coil of wire here. Now remember, for a single loop of wire, we could use Ampere's law to determine the magnetic field inside that loop of wire. or BS of R, pardon me, to determine the magnetic field inside the loop of wire. And imagine we've got all these loops that are stacked along each other. So, right next to each other. And I've drawn them with significant distance apart, but in a true solenoid, they are packed right on top of each other. They're thinly insulated wire. They almost have like an enamel coating, like almost a paint kind of insulation compared to the thick insulation that you may be used to. So let's look deep inside this solenoid to determine the magnetic field inside the solenoid. So again, let's have our current, and I'm going to draw these guys coming out of the page up here and into the page below. And so I can make, because this is a very tightly packed coil, so imagine a tightly packed spring, and I can treat this shape as being pretty symmetrical. So remember, Ampere's law works for symmetrical items. So let's look at if this purple loop as being our closed path to integrate about. So remember, the magnetic field using Ampere's law is mu naught I, and this is the enclosed magnetic field along a closed line. This is the magnetic field strength, and this is dotted with the length. So let's treat this guy as having a length L here. And let's go around the loop just in a counterclockwise direction because I'm right-handed and I thought about that way. And then the magnetic field, though, inside the wire, remember, is very strong, and it's pointed in this direction here. So all along here, so this magnetic field is very strong. And then outside, the magnetic field remember, is approximately 0. So if that's true, then let's evaluate this integral to determine the magnetic field strength around inside this long solenoid. So let's first consider this loop. I'll call this A and B and C and D, the corners there. Now I can integrate from A to B and B to C and C to D and D to A to get my total line integral for this enclosed. And so remember, this is a very long coil of wires. These wires are packed really, really close to each other. There's no distance between them. So if mu naught I enclosed is equal to the closed surface integral, then I can set it as piecewise from A to B. And in this case, the magnetic field here is parallel to L. And so the dot product of DL and B at that point will just be B DL cosine theta, because they're parallel with each other, and the angle between the magnetic field and that line segment there is 0, and the cosine of 0 is 1. So then I can write this as just B DL. And I'm going to add to it the line segment from B to C. Now let's look at B to C a little closer. And so let's just zoom in here for the time being on one of these sets of wires here. And so let's look right between these two wires. Now remember, they're very close to each other. So close that they're only separated by like almost a paint, that an enamel, like almost nail polish. I can't think of the thing that you might have seen, but to insulate it. So they are super close to each other. And at this point right here, since the current is out of the page towards you, your fingers would wrap around and up right there. So due to this piece of wire here, you would have a magnetic field directed up. Okay? Now, let's consider this one over here, also out of the page. And as you wrap your fingers around it, the magnetic field is, counterclockwise here. And so the magnetic field contribution due to this piece over here would be down. And so essentially what we get between the two wires along the BC length is zero magnetic field. So then I would have, a zero magnetic field contribution along the BC line. Then I'm going to add to it the integral of C to D. And again, we have assumed that the magnetic field outside is so small compared to what's inside because of all the contribution, the superposition of the magnetic field due to the coils there. And then if I add to that from D to A, completing my circle or my loop here, I can use the same argument along the D to A line as B to C, and that the magnetic fields would cancel out there, and so then I get plus 0 there. So what do I get? I get that the mu naught I enclosed is equal to the integral from A to B, B dl. So let's look at that in depth here. And so the current enclosed by this loop is a little different. So since we're only looking at this bit of, or this Amperian loop here that's purple, the magnetic field, or the current, enclosed by this Ampere's loop there would be the number of these loops times the current in each one of them. And so here, the mu naught, and then I enclosed will be the number of loops times I, the current through the whole solenoid. And we're going to go from A to B. And in my example, A to B is this length here. So I'm going to make that substitution. And then it would be B times L. And so then the magnetic field deep inside the solenoid would be mu naught N times I, the full current through the solenoid, divided by the length. Now a lot of times this number of loops which should be represented by a capital N, so I made that correction there. So the capital N is the number of loops, and L is the length of that. Now, in order for this magnetic field equation to work, the radius of the coil has to be much, much, much smaller than the length. So again, think about the springs that we've used in lab before that are small, tightly wound springs. And so this number of loops per length is sometimes written as little n. So that's the sort of the loop density, if you want to call it that. And then that means that our magnetic field deep inside a tightly wound coil of wire solenoid would be mu naught little n times I.